Okay, so welcome everyone to the first problem solving live session of this course, Viscous Fluid Flow. As you know, the course code is ME333 and this had been, so we are in 2026. So I think the whole course code with the year is NOC 26 ME33. And as I said, this is going to be a problem solving session. So I've also posted the notification of it in the discussion forum of this course. So first of all, I am Raj Nandan from the Department of Mechanical Engineering, IIT Gandhinagar, and I am a PMRF TA assigned for this course. So typically, as a part of my PMRF requirement, I also need to. So I also just one second. Okay, so as I was saying, I was just introducing myself. So as a part of my PMRF TA requirement, I also need to carry out TA duties online, for which I prefer to do these kind of tutorial sessions in NPTEL. So one, it serves my purpose of fulfilling my TA duties, and the second, I also get to interact people like you who take these wonderful courses of NPTEL and carries the legacy of NPTEL forward. Okay, so basically, some announcements before we formally set to start these session. So first of all, we are primarily going to meet on Saturdays from 3 to 5 p.m. As we are here for the first class. So from the next Saturday onwards, also we are going to meet from 3 to 5 p.m. using the same link that you are provided for this class, which means that throughout the entire tutorial sessions or whatever amount of tutorial sessions we will have, we will always join with the same link. Okay. And although we are saying that, okay, we are always going to meet from 3 to 5, so there can be some emergencies from my end for which I may require to reschedule the sessions. That is not always the case. That is very rarely we will do that, if at all there is a need that arises. However, if there are any rescheduling that is to be done from my end, you will be intimidated a priori at least, couple of days ahead. Don't worry about that. You will be intimidated through emails. You will so the reschedule time will be posted in the website, and also I'll separately post it in the discussion forum. That being said, if nothing else is announced, remember always we are going to meet on Saturdays from 3 to 5 p.m. For the live interactive session. Okay. The second thing is, although we are meeting from 3 to 5 p.m., it's not that hard and a fast rule that always we are going to sit here for 2 hours. I understand that's a little bit of long time, and that sitting 2 hours at a stress and solving problems online, I understand it's too much of a task to ask. But given that everyone is gelled, I mean everyone is here, and so long as we are enjoying enjoying the hours, we will be here. Let's say for around 1 I mean let's say we'll be here for around 1 hour 30 minutes or 1 hour 45 minutes, whatever is the time. But the allotted slot is 2 hours, so we will see that if if things are going well and everyone is on the same wavelength, then we will continue the session to maybe 1 hour 45 minutes or 1 hour 30 minutes. But like if you feel that things are getting too heavy for the session, because I understand this is little bit of an advanced level course, so there is going to be a lot of maths involved. So if things are getting heavy, then you can always let me know that, okay, let's call it a day, and we can then start it from the next tutorial session onwards, or the next discussion hour onwards. Okay. So as I said, it's not that you always need to be sitting here for 2 hours, and it's nothing like that. So it's kind of a learning, so we will try to have fun along the way. Okay. uh, the third thing is, these sessions that you are here for, these will be recorded, okay, and they will be posted in the course website. Okay, so the session that we are holding today, these are recorded, so I am doing the recording from my end, and I will share it to the NPTEL team of the course, and they will separately post it in the course website. At the same time, the notes that I am going to write here, they are also going to be, I mean the notes that I will base primarily write, so I'll just write on my iPad. So whatever I'm going to write, these are also going to be, made available to you, uh, as I said, in the website as well from the NPTEL team. So I'll be sharing all of this once a particular session ends to the NPTEL team of this course who is assigned for this course, and then he or she will, update this in the course website. But this doesn't mean that you will just skip the session, or you will not just attend live sessions. So I hope you understand that the main lecture series of these sessions are recorded, so you don't get to interact with the professor, uh, who is basically teaching those live, teaching those main contents or the theory of the course primarily. But this is where you actually get a chance to interact with the course members, and clarify your doubts. So this is why these sessions are kept. But at the same time, we understand that we have a very diverse set of audience here, coming from institutes, coming from academia, coming from industry. So, everyone have their availabilities and time slots. So keeping that in mind, that was the idea behind, doing this recording. Uh, but as I said, try to attend the sessions whenever you are available to do so. Okay. So that's the third thing. And finally, and a couple of quick things. So whatever we are going to solve, uh, of course, this is a problem solving session, as the name of the session suggests. Okay. So needless to say, we are not going to dwell much in the theory of the problems, because that is something that we will already learn in the lecture series or the video series of the professor. Uh, so I expect that whenever you come for this problem solving session, you at least go through the lecture series video of the particular week. For instance, today we are going to start with week 1. So I expect, and I am hopeful that you guys have at least gone through the material of week 1. So the idea is primarily because it is not possible to discuss the theory in just one session of a particular week. That is not possible, and for that you have the lecture series. The idea of these sessions is to solve problems that are associated with the concepts that you learned in the videos of the lecture series. Okay. And that being said, I hope you understand that your assignments are due in I think in the coming days. Okay. So the idea of this of the problem, so the nature of the problems that I'm going to show you, or that I'm going to solve for you, they are exactly not going to be the problems that are given in the assignment, because that doesn't serve the purpose, right? If I solve for you the assignment problem, that there is nothing left for you to solve, right? So we will not exactly solve the problem that are there in the assignment, but because that primarily is for you to solve. Okay. But the idea is, so I have picked problems, or I have certain problems with me that will be similar to the problems that are there in the in that particular week's assignment. For instance, you will see, if you have seen the assignment, that the problems that I'm going to solve, they are not exactly the problem from the assignment, yet they will be very similar to the problem that you are going to solve for the assignment. Which means that if you pay attention to the math that we'll be doing here, or to the problem that I'll be solving here, then I expect and I believe that you can easily tackle the problems that are there in that particular week's assignment. For example, the problem that I'll solve today, it will be very much helpful for you to solve week 1's assignment series. Okay. And that will be what we will be doing in all the subsequent weeks that follows. Okay. So these are some bookkeeping stuffs that I thought of saying before formally starting the course. Again, I am Rajnandan from the Department of Mechanical Engineering, IIT Gandhinagar. So the area of my research, so I primarily work on something known as low Reynolds number hydrodynamics. And I'm an analytical and a numerical guy. So I don't do experiments, but I solve things analytically and numerically, as a part of my research. And you might have also known that the professor associated with this course is Professor Amarish Dalal from IIT Guwahati. So typically the lecture series that you see are his videos, and I will be your TA who will be helping you to solve the problems. Okay. So with this, let's get started. I'll not talk much and just get down to business. So, but before that, if you have any questions, you can feel free to, you know, ask me, or you can type in the chat box, whichever way is convenient for you. I'll stop here maybe for a couple of minutes, and then I will start with the contents of this week. As I said, in the meantime, if you have any questions, you can feel free to let me know. Okay, if no questions, I hope things are pretty clear as of now. So let's get started then. So if you have gone through the lecture series videos, so primarily in the first week, it was just the recapitulation of the fluid mechanics that you have learned in your undergraduate fluid mechanics course. Okay. For instance, you learned about something known as, I mean, the basic idea of fluid kinematics. You learned something known as the streamlines, something known as vorticity, and then rotational velocity of a fluid element, and something known as the substantial derivative uh, associated with these streamlines. And finally, you learned something known as the Reynolds transport theorem, which I have written here. And as you will see, basically that's a gap, or that's a, so what I interpret Reynolds transport theorem as a bridge that connects a controlled mass system to a controlled volume system. And believe me, even though it is very simple and it comes from the from the first principle, this theorem is actually very powerful. Okay, and all the, most of the governing equations that you see uh, in fluid mechanics, where we actually write Eulerian descriptions, so they are primarily derived by using the Reynolds transport theorem. For example, the most simple, I mean, I won't say that simple, but the most fundamental equation of fluid dynamics, which is known as the continuity equation, that can be derived if you conserve mass using the Reynolds transport theorem. Okay. I believe the derivation is already been done in the lecture series. So as I said, we'll not be dwelling into the theory much, but as and when, I feel that some recapitulation is required, I will, give you a flavor of what has been done in the week's lecture series. Okay, so these are the two things that we learn. And as I said, in since this is the very first class, or the very first session, we will keep things very simple. I will go very slowly. And if you have any doubts, as I said, feel free to interrupt me at any point of time, and I'll be happy to address the queries. Okay. Okay, so we'll start off with solving problem with these two concepts. And so primarily we'll start off by looking into fluid kinematics, like solving for, the vorticity, given there is a flow field. We'll learn about something known as the substantial derivative. For instance, if the velocity field is known, what will be the acceleration and things like that. And then we'll be solving two problems associated with the Reynolds transport theorem, which is primarily, so in this session, we'll only see conservation of mass. And I believe there's a problem in your assignment which is very similar to one of the problems that I'll solve for the Reynolds transport theorem. Okay, so that's the idea. All right, so let's get started. So I have written the questions a priori, but the solutions I'll be doing live, as you will see. Just to save time, I have written the problems which you can see on your screen. So let's uh, read this problem and let's try to see a possible way of finding the solution. Okay, so it says that there is a velocity field in a fluid medium whose component wise description is given by 3x square y ex plus 2xy ey plus some 2zy plus 3t ez. Okay, where I hope you understand that this ex, ey, and ez, these are nothing but the unit vectors. So this I clarify this, that this ex, ey, ez, these are nothing but the unit vectors. And I hope you realize that these are same as the more conventional I hat, j hat, and k hat. So instead of writing I hat, j hat, and k hat, I have written it as ex, ey, and ez. But don't confuse them with any other thing. These are just the unit vectors whose magnitude is just equal to unity. Okay. So given this velocity field, what they're asking is, they're first asking us to calculate the rotational velocity, okay, and the vorticity. Okay, so it's that simple. They're just asking you to calculate the rotational velocity and vorticity, but you can only calculate them when they specify you a certain position, and you can see that this particular velocity field is unsteady in nature because there is a t term here that is coming into the picture, which means this is a non-uniform and an unsteady velocity field that they have given. So that's the reason why they have asked us to evaluate these quantities at this position and at time t equal to 3. Okay, so that's what they're asking. All right, so first of all, going into the solution procedure, I have couple of questions that I want, uh, if you can, that I want should be discussed. Okay, first of all, can you tell me that the description of velocity field that uh, we have seen here, is this a Lagrangian or an Eulerian description? That's my first question, because this will then help you to understand how are we going to calculate the required quantities that the question is asking us to solve for. So I hope my question is clear. So the question is that the velocity field that is given here, is this a Lagrangian or an Eulerian description? That's the question. Okay, so so the answer is, you first need to see how is the velocity field represented. Okay, so just doing a quick recapitulation, if you have watched the lecture series, so if you have a Lagrangian field, it means that you are just interested in one single fluid particle, and what you try to see is, you just try to see that a single fluid particle is something that you are interested in, and then you see that how this single fluid particle basically moves in space inside the fluid. Okay, so so typically, if you are doing that, that description becomes a Lagrangian description, which means if you are associating a unit vector, or let's say if you are associating a position vector to this fluid particle, let's say I'm naming it as p, and the associated position vector I'm naming it as x bar, then that position vector is just going to be a function of time. Okay, because what you are doing is, you are essentially seeing how just one single fluid particle basically moves in space, and that's something that we call it as the Lagrangian description. So things in Lagrangian description become just a function of time, because instead of focusing on a space, we are just looking into one single fluid particle, and then we are trying to assess how the position of that fluid particle becomes a function of time. So it's like at multiple time stamps, we are seeing how the position of that fluid particle basically changes. However, if we are in the Eulerian description, or if we are in the Eulerian field, okay, then what we see is, instead of confining our attention to just one particle, we fixed our space, we fixed what to say, our position of the viewpoint, and then we see whatever dynamics that happen in that particular fixed frame of reference. Let's say, for instance, in order to make things to be more clear, instead of focusing on one single particle, we see that, let's say I fix a particular, let's say, segment of a pipe, and then I see, so let's say there is a pipe flow, just to make things clear, then I say that within this particular segment of the pipe, denoted by this dash line, I try to see what's the dynamics inside this particular segment. That's typically what is denoted by the Eulerian description. So now, instead of things being a function of time, naturally things will now be a function of space, because I'm fixing my space here, to be very precise. Okay, for instance, if I want to look at the velocity field, I will say that, okay, the velocity field within this segment is just going to be some function of x. That's it. Okay, so the primary description is, now instead of focusing on just one single fluid particle at different instance of time, we rather fix the space and then see how many fluid particles basically have entered this space, and then how many fluid particles basically have left this space. Typically, that's what we do if we are looking into an Eulerian. Sorry, this spelling is wrong for Lagrangian. And this description, we call it as the Eulerian description. Okay. So given this, if you look at the velocity profile, you can typically see that your velocity components, for instance, the u component of velocity, that is the the x component of velocity, which we denote it as generally u. So if you look at this velocity profile, the x component of velocity which we generally denote it as u, this is equal to 3xy squared. Okay. So naturally, this is an Eulerian description, right? Because you can see that when you are moving, when you are actually changing x and y, you can see that your flow field has actually changed. Okay. This is the classical description of a non-uniform, flow field in Eulerian coordinate frame, basically. Okay. But if you look at now, so similarly, if you want to look at the y component of velocity, this is going to be 2xy, as you can see from this. Okay. It's going to be 2xy. Okay, and similarly, if you look at the z component, the z component of velocity is going to be 2zy plus 3t. Okay, so this is going to be 2zy plus 3t. Okay, here is something where you need to be a little bit careful. See, if you look at the x component, you can see that this is just a function of spatial variable, for instance, x and y. For example, you can interpret like this is kind of, so you can think of it like, you have a pipe which is basically going in the 3D direction as well. Okay, and so this is kind of like the height of the pipe, and basically you can think of it like this is x, this is y, and this is z. Okay, so then you are kind of having a flow which is moving, which is coming inside the pipe. Okay, whose x component is given by this, y component is given by this, and z component is given by this. Okay, so what I was trying to say is, if you look at the x component, you understand that this is just a function of space. And similar is the y component, because it is just dependent on x and y, which are primarily the independent variables. But if you look at the z component, you can see that there is an inherent dependence of time. Okay, which indicates that the flow field that we are looking here is unsteady in nature. That is natural, because if you put a different value of time, you will see that you will have a different value of z, different value of w, to be precise, which means that the flow field that you are given, it's kind of an unsteady flow field, and precisely it's so dependence of time through the z component of velocity. Okay, so I hope the description of the flow field is clear at this point. Okay, any questions? All right, I feel there is no questions. So so okay, so that's the given problem. Okay, we have not still evaluated the solution, but that's the given, at least the physical picture of the problem, and I hope that is clear to you. Okay, now given these things, what they're asking us to calculate the rotational velocity. Okay, so that's simple. So now if we know the velocity field, we know that the rotational velocity, which we call it, people may call it as omega, I generally call it as w, and I understand, and I hope that you understand that the rotational velocity is going to be a vector. Okay, and this is given as half of curl of the velocity field. Okay, that's precisely is what the rotational velocity is. Okay, so that's the rotational velocity. Okay, I hope this is clear. So for the ones who just now joined, we are just solving the first problem, and the problem is kind of like a straightforward, just restating it, because for the ones who have just now joined. So what we are doing is, we are looking into a velocity field. Of course, in Eulerian description, I have just now explained why this is the case of an Eulerian description. And then what we are asking is, what the question is asking is to calculate the rotational velocity and the vorticity at this space and at this particular instant of time. Okay, so the rotational velocity is just going to be half of curl of velocity. And so what we need to do is, because we know the velocity field, because the velocity field is going to be what, so v is going to be u times ex plus v times uy plus w times ez. Okay, where u is basically equal to this, v is basically equal to this, and W is basically equal to this. That is I mean, the field is basically given in your question. That is what I'm trying to say here. So what we need to do is we just need to evaluate the curl. That's it. So any idea how we evaluate the curl here? Or in other words, we just need to evaluate this quantity. Okay, I hope you guys at least know how to evaluate this curl. So basically what I need to do is we just need to evaluate this. So this is going to be, so this is something that how curl is evaluated. So you write the unit vectors ex, ui, ez. So ultimately what you're doing is you're evaluating the cross product between the del operator and v. That's what you're doing. Okay, so the del operator, so this del operator, this has, you know, this has components like del del x, del del y, and del del j. Okay, because you can write your del operator as del del x ex plus del del y ey plus del del z ez. And then what we are doing is we are just taking the curl between this and the velocity field. That's all that we are doing. Okay, and then the other three components will be u, v, and w. This is going to be u, this is going to be v, and this is going to be w. And what we need to do is we are just required to evaluate this. Okay, so I hope you know, and this is like elementary fluid mechanics that you learn in your first or second year of your BTech. So this is primarily going to be, so in the first direction you are going to have ex, and u is going to come over here, and v is just going to go over there. So it is going to be del w, sorry, I said u, it's actually w. So it's going to be del w by del y minus del v by del z, and the direction is going to be ex. Okay, similarly, if you are choosing this, it is going to be w, it is basically going to be w going over here and u basically going over there. So this is going to be what? So this is going to be del w by del x minus del u by del z, and then this is going to be your ey. Okay, and your ez is going to be what? So this is going to be del v by del x minus del u by del y. Okay, that is simply what this is what you're doing. So you are choosing ez, so this is going to be del v by del x minus del u by del y. That's all that you're doing. Okay, so what you are essentially doing is you are writing your omega as a curl of the velocity field. It's actually half of the curl of the velocity field, where curl of the velocity field is going to be just this. Okay, so equivalently, I hope you can understand that we can then write omega, which is the rotational velocity, as omega x ex. This is not going to be a vector because I'm considering it as a component. So this is going to be omega x ex plus omega y ey plus omega z ez. So what we are doing is we are just replacing this with omega x, we are replacing this with omega y, we are just replacing this with omega z. And then if you just do a simple comparison, you will see that your omega x basically is this term. Okay, this is going to be your omega x. So this is what? So this is del w by del y minus del v by del z, and your omega y is going to be this quantity. But remember, there is a half here. Okay, remember there is a half here, so we also need to account for the half. So it's going to be a half multiplied by this quantity. Okay, it's going to be half over here. Okay, similarly, omega y is going to be this times half. So it is half of what? Del w by del x minus del u by del z. Okay, and wz is going to be half of this quantity basically. So del v by del x minus del u by del y. So it is going to be del v by del x minus del u by del y. Just to avoid confusion, what I will do is, let's not call this as omega because there is a W already here. So I think we'll confuse the two quantities. So let's call it as something like this. Okay. So then this would be just, so we are denoting this by the symbol omega. That's what we are doing. Okay. Omega X, omega Y, and omega Z. And then these quantities will also be omega X, omega Y, and omega Z. So omega X, omega Y, and omega Z. Okay. Any confusion until this point? Please let me know, like, if there are any questions or suggestions until this point. And I mean, I don't know if you're clear or not, but how did we basically get this? Okay. Relations for omega X, omega Y, and omega Z. Is this clear or not? I mean, is this okay up until this point or not? If it would be great if you can let me know if this works or not. Okay, so I hope you can understand this. Yeah, okay, thank you. Yeah. Okay, all right. So what I need to do now is basically to evaluate these. So we have u, v, and w. We just need to evaluate these derivatives to basically get omega x, omega y, and omega a. That's all. That's all that we need to do. So let's calculate step by step. So for omega x, I need what? So for omega x, I need del w by del y. So let's see what variables do we need. So let's check from u. We require del u by del z, del u by del y. That's all that we require. So let's calculate that first. So we have u as what? So we have u as 3xy square. Okay. So if your u is 3xy square, your del u by del first, let's say the y is going to be 6 xy. Your del u by del z is going to be 0 because there is no z component here. Okay. Similarly for v, we have v as 2 times of xy, which means my del v by del x, because this is something that we require, is going to be 2y, and del v by del z is going to be equal to 0. Okay. uh, I hope this is clear until this one. Okay, please let me know if there are any errors in the math uh, while doing the math so that I can rectify. Okay, so I think this is clear. So if you have v equal to 2xy, let me check if this is the v or not. Okay, so v is 2xy. So your del v by del x is going to be 2y, and your del v by del z is going to be 0. Similarly, for w, which we have 2zy plus 3t, you can calculate del w by del x to be equal to what? So what is going to be del, so let's calculate del w by del x first. Okay, because I think we require del w by del x, right? See, yeah, we require del w by del x here. So del w by del x is going to be 0 because we don't have any x dependency in w, and del w by del y is going to be just 2z, if I'm not wrong. Yeah. Okay. Okay, so that's it. Then we have calculated all the quantities that we require here. So let's then just substitute. So your omega x, your omega x is what? So your omega x is half of del w by del y minus del v by del z. So it is going to be half of, it's just substitution. I hope this is clear to you now. Okay, it is going to be half of del w by del y minus del v by del z. Okay, and then if you substitute, this is going to be half del w by del y is 2z from this. Okay, and del v by del z is equal to 0, which means that your omega x is just going to be equal to z. Okay, similarly, if you calculate omega y is what? It is half of this quantity is omega y, which is del w by del x. Remember, there is a minus as well. Okay, so it is going to be minus half del w by del x minus del u by del z. It is going to be minus half del w by del x minus del u by del z, and if we just substitute, it's going to be minus half of del w by del x is equal to 0 from here, okay, and minus del u by del z is also going to be equal to 0, so this is just going to be equal to 0, which means this is 0, so your omega y is just 0, okay, and your omega z is going to be 1, so this is going to be this quantity, so it is half of, okay, so this is going to be half of del v by del x minus del u by del y, and then let's just substitute the values as we had been doing. So del v by del x is going to be what? So your del v by del x is going to be 2y, okay, minus del u by del y. Your del u by del y is this, so it is 6xy, okay, it is 6xy. Okay, all right, that's it. So that's the rotational velocity. So since we know that the rotational velocity is going to be omega x ex plus omega y ey plus omega z ez, and we know that omega x is equal to z, omega y is equal to this, and omega z is equal to this. But remember, we are not done yet because we are yet to substitute the value of x, y, z and time basically. Okay, so that's what they're, because remember the question, that's what they're asking, right? They're asking us to evaluate these quantities at 1, 2, 1 and t equal to 3. Okay, so basically what we need to do is we just need to substitute x as 1, y as 2 and z as 3 and t as 3, but we don't have sorry, z as 1 and t as 3, but we don't have explicitly dependence on time basically, so t equal to 3 is immaterial here basically. Okay, so what we now need to do is substitute x comma y comma z as 1 comma 2 comma 1, and if you do this substitution you will see that your omega x is equal to, so your omega x is z, right? This is just, oops, sorry, your omega x is just this, so this is just going to be 1. Okay, similarly, because z is basically equal to 1, that's what we have in our problem, right? Z is 1 and your omega x is just z, which means that your omega x at z equal to 1 is just going to be equal to 1. And similarly, your omega y, we all know that is 0, and omega z is going to be okay. So what is going to be omega z? So let's see. This is going to be half times, you need to substitute your y to be equal to 2, which means this is going to be equal to 4, minus you need to substitute your x to be equal to 1 and z to be equal to sorry, y to be equal to 2, which means this is going to be equal to what? 6 times 1 times 2, which is going to be 12. Okay, which means that your omega z is going to be minus 8 by 2, which is going to be equal to minus 4. Please check the math, and if I am doing anything wrong, let me know in the algebra. Okay, so that's it guys. Then finally we have the rotational velocity omega. I hope you understand that rotational velocity is a vector which is equal to omega x ex plus omega y ey plus omega z ez, and if you substitute the value, this is going to be equal to ex, omega y is 0 and omega z is minus 4, so it is going to be minus 4 times ez. That's it. That is precisely your rotational velocity at, you know, x comma y comma z equal to 1 comma 2 comma 1 and at time t equal to 3, given that you have a flow field in Eulerian form of the form uex plus vui plus wez. Okay, where u, v, w are the components of the velocity in the x, y and z direction. I hope this is clear up to this point. So please let me know if you have any questions or queries up to this point, and then we'll evaluate the second part. Okay, so I think things are clear up to this point. So basically, the second part is very simple. They are just asking you to calculate the vorticity at the same points. So since you just require to know the vorticity and you know the rotational velocity, so there is a very simple relation that your vorticity your vorticity, remember vorticity is also a vector. Uh, I generally denote this as a capital gamma, and this vorticity vector, so you can denote it with any symbol. I generally denote vorticity as capital gamma. So this vorticity is equal to 2 times of the angular velocity, and you know that your angular velocity is this, which means that your vorticity is going to be 2 times ex minus 8 times ez. That's it. That is, so this is your angular velocity. Oops, sorry. So this is your angular velocity, and this is your vorticity. Yeah, okay. So you're asking the difference between rotational velocity and vorticity. Yeah, so okay, I'll come to that. Okay, so that's a subtle point actually. So there is physically there is nothing any such difference between rotational velocity and vorticity. Okay, you can equivalently say that a flow field with this much of vorticity will also indirectly possess a rotational velocity. It's just that people have defined vorticity as 2 times of rotational velocity, and it is just the same quantity that just differs by a magnitude of 2. That's it. I mean, there is nothing else. It is more convenient actually. You will see that in certain places, if you take twice of this quantity and then define a new quantity known as vorticity in certain instances. But apart from that, there is no qualitative difference between angular velocity and vorticity. Qualitatively, they are just the same. Quantitatively, it is just half of the one another, or vorticity is just 2 times of the angular velocity. I hope that this answers your question. There is no qualitative difference between angular velocity and vorticity. Does it answer your question? See, vorticity, is morely associated with circulation, and you can equivalently calculate the angular velocity associated with that as well. It is just that factor 2 that comes, and apart from that, there is nothing, to the best of my knowledge, there is nothing as such qualitative difference between angular velocity and vorticity. I mean, does this answer your question? Okay. Okay, all right. Okay, then let's. Okay, so this is a very easy problem, but I have done it very slowly. Given that this is a first problem, now we'll, quantitatively like increase the pace. Okay, so then we have a problem. As you can see, this again is a very simple problem. So what they're saying is that the velocity and the density fields in a diffuser are given by, so this is your velocity field and this is your density field. Okay, so the field variables are given, and I hope you can. Because now, can you tell me, is this an Eulerian description or this is a Lagrangian description? Can think about it and tell me that the velocity fields or and the density field, is this an Eulerian description or this is a Lagrangian description? See the dependence of velocity and density on the variables. I hope you realize that this x is a variable which is the field variable, uh, and then is this a Eulerian description or a Lagrangian description? Can you tell me? See, this is an Eulerian description, right? See, again, I am stressing on the fact that in Eulerian description, it's like you are not focusing on just one particle. You are just focusing on a region of space basically, and you are seeing that you are basically seeing the number of particles coming in and the number of particles basically going out. Okay, so whenever you define something known as a field variable, these automatically hints that it's a Eulerian description, because you have defined something as a function of a field and not just a function of one single coordinate of a particle, which is just a function of time. Okay, so whenever you see only explicit dependence of time, then only it is your Lagrangian coordinate typically. If you see like variation in space, and it can sometimes be in addition to variation in space, some additional variations in time, and if you are given that these are field variables, it should be automatically clear that this is basically it's an Eulerian description. because you are not just focusing on one single fluid particle, you are basically focusing in a region in space. Okay, I hope this clarifies your. So this is the most fundamental uh, difference between Eulerian and Lagrangian descriptions. Okay, so I hope you realize that this is an Eulerian description that we are given here. Okay, so given this, they are asking us to calculate what is the rate of change of density at x equal to L. Okay, so because we are in an Eulerian field, okay, because we are in an Eulerian description, in order to evaluate the rate of change of density, we need to calculate something known as the substantial derivative, basically. Okay, sometimes they are also called as the material derivative. Okay, so what the question is asking us to evaluate capital D rho by capital dt at x equal to L. That's what the rate of change of density at x equal to L signifies in an Eulerian description, basically. Okay, I hope this is clear. This is not equal to, remember, this is not equal to d of rho by dt. This is precisely a Lagrangian description, and this is completely wrong if you are given field variables and you are asked to calculate the rate of change of the field variables, because the concept of field variable itself comes in an Eulerian frame, and in order to evaluate the rate of change, naturally they will have distances, for instance like this x, which is a distance basically. This means that you are asked to calculate the material derivative, to be very precise. Okay, that is what the rate of change of density at x equal to L signifies. Is this clear or not up to, up to this point, that why are we calculating this d capital rho by dt? Okay, yeah, nice. Okay, all right. So then we will now, so this, this is known as, so whatever we have written it, this is known as the substantial derivative, or sometimes, so it's called the substantial derivative, and sometimes they are also called as material derivative. And when you evaluate the material derivative, I hope you are clear that this is going to be del rho del t, because your density in principle can also be a function of space and time, plus in vectorical form, this is denoted as v dot grad. This delta is called grad, and this is operated on rho. Okay, this is precisely what material derivative looks like in Eulerian description, of course. Now, this quantity del rho del t, this quantity, you know what this is saying? This is saying that what is the partial change of density with respect to time? That's what they're saying, and this is known as temporal derivative. And this quantity v dot grad, so this is v. Remember, I'm writing this in vector form. Okay, I'll expand this and show it to you how this look like in component wise form. But in shorthand notation, I'm just writing this in vector form. So this is v dot grad evaluated on the density rho. Okay, and basically this is known as this quantity. This is known, so this is known as the, so it's kind of a spatial derivative, or sometimes they're also known as the convected derivatives, basically. So it's better to call it as spatial derivatives. Okay. So you can understand that the temporal derivative and this v dot grad rho, this constitutes the substantial derivative or the material derivative. Okay. Now then let's calculate this. So I hope you can understand that in our case, this quantity is just going to be equal to 0. The reason for this is the fact that your density is just a function of space and not a function of time. Okay. So for us, this quantity is going to be 0, and we are just required to calculate this quantity precisely, v dot grad rho. Now, you need to understand how this v dot grad rho essentially look like. Okay. So you can write your v as so basically this v is vector form in component form, just like in the previous example. You can write it as u times ex plus v times uy plus w times ez. See, all we are doing is we are trying to calculate this v dot grad rho. We are basically trying to simplify this. Okay. And then I'm writing v at this. Now see, before substituting this on or operating this on the density, there is a dot product between the velocity field and the gradient operator. Okay, so The gradient operator, as I said, I also showed it in the last example. This gradient operator looks like del del x ex plus del del y ey plus plus del del z ez. Okay, so this is how the gradient operator looks like. So now if we are to calculate a dot product between v dot del, then what is it going to be? So all we need to do is evaluate v dot grad. That's what we need to do. Okay, so then if you pay closer look, what we are doing is we are just essentially calculating the dot product between this vector and the gradient operator, which itself is a vector. Okay, and then the dot product of this, I hope you can understand, then this is just going to be u del del x plus v del del y plus w del del z. This is just going to be the dot product of v dot grad basically. Then that's simple, right? Because this is ex and this is ex, so ex dot ex is 1, and then you will have u times del del x. You cannot have a non-zero dot product between this and this, because we already know that if we have two orthogonal unit vectors, their dot products are basically equal to 0, meaning that since ex and ey are perpendicular to one another, their dot products are just going to be 0, which means all we are going to get at the end of this is going to be u del del x, v del del y, and w times del del z. It is that simple. Okay. All right. So now what we need to do is we just basically need to substitute this. I mean, take this v dot grad and operate this on the density function, or the field variable denoted by density. So therefore your v dot grad. So therefore your v dot grad of rho is going to be what? So this is going to be yes. Any questions?
No, no, sir, no.
Oh, okay. All right. Then this is going to be what? U del del x of rho plus v del y of rho plus w del z of rho. Okay, I hope you were with me on with this so far. So is this clear or not? Like, how did we get this v dot grad rho? Is this clear or not, basically? Yes, nice. Okay, very good. So that's it then. That's all we need to do, right? So now we have rho equal to what? Rho equal to rho naught. We have this, right? Rho naught times e power minus x by L. So this is going to be rho naught times e power minus x by L. And we just require to evaluate these quantities. And given that we have the velocity field, so velocity field is also given. Your velocity field, remember, is just an x component velocity field, which is u equal to u naught times e power minus x by L. Okay, so u equal to u naught times e power minus x by L, and it is given that your v is equal to 0, w is also equal to 0, which means that these quantities are basically equal to 0, and your d rho dt is going to be just u times del rho by del x, right? Because this is anyway 0. This term is anyway 0 because of the fact that your rho is just a function of space. And we have seen that we don't have a v and a w component of velocity, which means that your d rho dt just simplifies to u times del rho by del x. That's it. And then we just substitute. So u I know is u naught times e power minus x by L, and del rho del x is what? We just need to differentiate this with respect to x. So what does it become? So del rho del x is going to be what? Minus of rho naught by L times e power minus x by L. Just differentiation with respect to x. That's it. So this is going to be minus of rho naught by L times e power minus x by L. Hold on. Did a mistake here? Okay, so I forgot. In U, you have a minus twice x of L. Okay, so this is actually minus twice x of L, and this is a minus twice x of L. Anyway, this is just a typo that I did. Okay, so your del rho del t, which is the substantial derivative of density, is then going to be minus rho naught u naught rho naught by L times e power minus thrice x by L. But remember, we are asked to evaluate this. We are basically asked to evaluate this d rho by dt at x equal to L, right? So then we just need to substitute the value of x at x equal to L. That's all that we require to do. So your d rho dt, that is the substantial change in density at x equal to L, is going to be minus u naught rho naught by L e power minus 3. That's it. So what you need to do is you just require to substitute this x as x equal to L. Then this L and this L would basically cancel, which just comes out to be equal to e power minus 3. That's it. Okay. I hope this is clear. Let me check if so it's this and this. Okay. I think this is fine. Okay. So that's it. So if you kind of, yeah, exactly. So if you kind of simplify, this is going to be d rho by dt at x equal to L is going to be minus of u naught rho naught by e cube L. That's it. That's it. So basically, this is precisely your change of density, which is in Eulerian field at x equal to L, is just minus of this u naught rho naught by e cube times L. I hope you can realize that these are just mere constants. Okay, this u naught and rho naught, these are some arbitrary constants that are given in the question actually. You can fit some values to them, but I mean, these are just some constants. It should not be a problem at all in this case. Okay, all right. So that's it then. This is precisely, I hope this is clear. And then let's move ahead. Now, I think we have done some fair amount of problems. So let's tackle the next problem now. Uh, so as you can see from your screen, this is a similar kind of problem to the one that we did. But now, we in the previous problem, we had density. So the material derivative, so we basically took the material derivative of a scalar. In this problem, what we will see is we'll take the material derivative of a vector. And what this problem is then asking us to do is, it's the same. Given there is a velocity field, you can see that this is an Eulerian velocity field. It's an unsteady field because it has explicit dependence on time. It also has obvious dependence on space. So it's an unsteady and a non-uniform velocity field that we have. What they're asking us is to evaluate the acceleration of a fluid particle at x equal to 2, y equal to 4, and z equal to minus 4, and at time t equal to 3. That's it. That's all that they're asking. Okay. So I hope the question is clear. It's a straightforward question. Given a velocity field in space which is non-uniform and unsteady, and we are required to find the acceleration of a fluid particle. Okay, so I hope you realize that this is similar to the last problem, except that in the previous problem we have taken the material derivative of density. Now in order to get acceleration, we need to take the material derivative of velocity. But the difference is that density was a scalar quantity, velocity is now a vector quantity. Okay, so your acceleration is going to be the material derivative of velocity with respect to time, and then again this is just as we wrote, that del v del t plus v dot grad. But remember, now we are operating this v dot grad on v basically. So this is a velocity. So basically this is a vector, and this is the small minute difference that we have with respect to the other problem. Okay. Okay, that's it then. We just need to evaluate this at x equal to 2, y equal to 4, and z equal to minus 4. Okay, so then let's do this. First of all, we already know. Okay, let's do the easy part first. Let's first calculate what is del v del t. So your del v del t. So I can write my del v del t, because remember, I can always write my velocity as we had been doing as u ex plus v ey plus w ez. Remember, and I hope I don't need to reiterate this, whenever I write a quantity with a bar, this means it's a vector. And in three-dimensional, it is going to have three components. You will see that later on, when I write a quantity by two given bars, by two bars, this will mean it's a tensor. It's a second order tensor. Okay. If I don't write with any dash, for instance, I wrote density as just the rho, this means it's a scalar. Okay. So a quantity without any bar, I will call this as a scalar. A quantity with a bar, this is a vector. And you know that in 3D space, vector is going to have 3 components. A quantity with 2 bars is going to be a tensor. And can you tell me how many components are going to be of this tensor in 3-dimensional space? For example, this A can be stress, like the hydrodynamic stress, which is a classic tensor. It's a true second order tensor. And can you tell me how many components will a tensor have in a 3D space? Just like a vector has 3 components, u, v, and w in 3D space, how many components is a tensor going to have in 3D space? Can you tell me? So think about it. I will take your answer in the next in the next discussion, in the next live session, basically. But anyways, we don't need to do that now. All we require is to evaluate this del v del t. So you can write your del v del t as what? So your del v del t is going to be del u del t. What we are doing is we are just substituting this over here. That's it. It is going to be del u del t ex plus del v del t ey plus del w del t ez. And let's see what we have. So we have u, the x component of velocity, as 4 plus xy plus 2t. So this is going to be 4 plus xy plus plus what? I think it is 2t. Yeah, 2t. We have v as the y component of velocity as 6x cube. 6x cube. We have w, which is z component of velocity, as twice x t square plus z. Is going to be twice x t square plus z. Okay, so let's calculate the partial derivatives with respect to time then. So your del u del t is going to be 2. It's rather straightforward. Del v del t. Can you tell me what is del v del t here? What is del v del t and what is del w del t? Given that we have u equal to this, del u del t, I already evaluated it for you. It is 2. What is going to be del v del t and del w del t? That's simple, right? You just need to know how to differentiate, how to basically do partial differentiation. That's it. You can at least give it a try, right? There is nothing wrong or I mean, there is nothing to be shy of when you are learning, right? Yeah, exactly. Yeah, that's it. 0 and 4xt. That's it. So del v del t is going to be 0 and del w del t is going to be 4xt. You just need to basically partially differentiate a multivariable function with respect to time. That's all that you need to do. Okay. All right. So then what do we have? So we have this means that my del v del t is going to be 2 times ex and v is going to be 0 and w is going to be plus 4xt times ey. That's it. Okay, that's the first part of this problem and that's the easy part. Okay, now we need to evaluate this quantity v dot grad of v. And this is the challenging part, because now we are operating this on a vector but not on a scalar, basically. Okay, so remember we evaluated this v dot grad from the last example. This v dot grad basically come out as u times del del x plus v times del del y plus w times del del z, right? So now this v dot grad of v, okay, this is going to be, see, I also need to write this v as uex plus vey plus wez, right? Because this is also a vector, which means that v dot grad v, that this quantity itself is going to be a vector, right? And this is obvious, right? Because see, this is a scalar and I'm operating this on a vector, which naturally means that the answer is also going to be a vector. Okay, so this is going to be, I mean, the whole quantity, this whole quantity v dot is v dot grad of v, this quantity is going to be u del del x of u plus v del del y of u plus w del u del z, and this is going to be the x component of this quantity v dot grad of v, plus the y component will be your u del v del x plus v del v del y plus w del v del z, and this is going to be your y component, and the z component is going to be u del w del x plus v del w del y plus maybe I'll write the z component with a different. Hey, it's okay, doesn't matter. Plus w del w by del z. This is precisely, this is precisely what v dot grad of v would look like if you expand it in the three-dimensional space, basically. Okay. I hope this is clear. See, this is simple, right? Because I mean, it may not be that simple when you're doing it for the first time, but as a fluid dynamics, like if you practice this like maybe a few times, this is just going to be a bread and butter for you, basically. It's just going to be that simple. Okay, so all we need to do is, I hope you understand that we basically require to operate this on the velocity v. But remember, now the velocity is a vector. See, in the previous example we had density, but so density was just a scalar. So we just had like u times del del x of rho plus v times del rho by del y plus w times del rho by del z. But now, since velocity is a vector, we must operate this on the three components of its space of the vector, basically, which means u is associated with one direction, v is associated with the other direction, and w is associated with the z direction, basically. And that's the reason why we are basically getting 3 because it's a vector. I hope you will see that you will sort of like this. You can also extend this for a tensor as well, and we will do that later on, but not now. Yeah, because this is the first. I mean, in fluid kinematics, at least in this chapter, we'll not look into the derivatives of a tensor as of now. Okay. Okay, then that's it. That's all required to do. We require to do, right? We just now need to evaluate these quantities del u del x, del u del y, and similarly these quantities. And we know that you have your u, v, and w as this. Okay, you just need to evaluate these derivatives: del u del x, del u del y, del u del z, and del v del x, del v del y, del v del z, and so on and so forth. Okay, and all you need to do is you just need to substitute x, y, z at so basically you need to substitute this at what? So you need to substitute this at 2, 4, and minus 4, and at time t equal to 3, basically. At 2, 4, and minus 4, and then you need to substitute time as t equal to 3. Okay, that's it. That's all will be your acceleration at this point and at this instant of time. I'll not do these derivations. I mean, these derivatives. I hope you are now fully capable of doing basically solving how to evaluate these derivatives. I leave it as an exercise for you. If you have any questions, you can let me know in the next discussion hour. Okay, but I hope this is fairly now straightforward. I have done the hard part. You just need to, yeah, go ahead.
So we will be having discussion in the next week also.
Yeah, we will. Yeah, we will.
Yeah, yeah.
Like,
Okay,
yeah,
okay.
at the same time. So I told it in the beginning of this discussion hour. It's actually at the same time from 3 to 5, and using the same link, basically. And of course, these sessions are also recorded. So the recording of today's session also you will get in the course website maybe in a day or two, basically. Okay.
Okay, we will get this recorded soon, sir.
Yeah, you will get it. Yeah, you'll get the recording. You'll also get these notes that I have written here. You'll get
Okay,
everything.
okay,
Yeah. Okay.
okay.
All right. Okay, so basically then you need to evaluate this quantity, and again you can easily do that, so I leave this as an exercise for you. You can then substitute these x, y, and z at 2, 4, and minus 4, and then get the acceleration at the required space and at the required time. That's it. Okay. All right. We'll maybe do couple of maybe 1 or 2 problems more, and then we will call it a day. But before this, if you have any questions, you can let me know. I'll take a short break. because it's very difficult to continue speaking for a long period of time. So I'll take a short break. In the meantime, if you have any questions, you can let me know either by
Yeah, yeah.
yeah.
Yeah, yeah. Okay, okay.
Okay, yeah. Okay, so the next problem is going to be on Reynolds transfer theorem, as I was saying. So we did a good amount of problem on fluid kinematics. Like we looked into something known as so basically what we did. So let's do a quick recap. So we looked into finding out the material derivatives of of what to say the field variables that we saw, and we also looked into like calculating the vorticity and things like that, the rotational velocity given a velocity field. Okay, we looked so these primarily constitute the fluid kinematics part. Now we looked into an important aspect associated with this as well, which is known as the Reynolds transfer theorem. Okay, and we'll try to solve a problem, a very simple problem, using this Reynolds transfer theorem. Okay, uh, I'll just come in 2 minutes. If you have any questions, you can type your questions in the chat box. I'll just come in 2 minutes. All right. Sorry for the interruption. So let's go ahead with this problem. So what we are primarily trying to do is look into the concept of the Reynolds transfer theorem. Basically, the Reynolds transport theorem is, so I interpret, kind of like a bridge. It connects a control mass system to a control volume system. You then need to know what the control volume system is. I hope that had been clarified in the lecture series. If not, so if you haven't gone through the lecture series, please go through it, uh, because then only it actually makes sense to solve problems in the in the discussion, I mean in these discussion hours. Otherwise it's difficult, because primarily in the discussion hours it is not possible to cover the theory of the problem. Okay, that basically is done in the lecture series. Okay, all right. So what basically we do in Reynolds transfer theorem is like it's a bridge that connects between a control mass system with a control volume system. That's what I said. Equivalently, you can say that it's a connection between a Lagrangian system and with an Eulerian system. Okay, and how these connections are made, uh, And this connection typically is the Reynolds transport theorem, as I was saying. Okay. So in general, the Reynolds transport theorem, actually, I'll write it down before me trying to solve this problem. So if you have a property, okay. So what this Reynolds transport theorem says, if let's say n is a property and this is an extensive property, so I hope you understand that any properties which are mass dependent, they are known as extensive properties. Okay, you can equivalently define an intensive property which then becomes the extensive property per unit mass, which then becomes an intensive property. Now remember that this extensive property and this intensive property, this can be anything. For instance, you can consider your n to be equal to, let's say, what? Maybe you can consider it as momentum. Then this becomes m times the velocity. Then the corresponding intensive property would be n divided by its mass, which just comes out to be equal to velocity. Okay, this is just one example that I'm showing. For example, you can consider n to be m times v. I hope you understand that m times v is just going to be the momentum. Okay, and then your intensive property just becomes equal to the velocity field. For example, you can also consider your n to be equal to mass. Then your intensive property becomes m by m, which is just equal to 1. Okay, but for any generic n, for any generic extensive property, you can then write that the rate of change of n with respect to time in a controlled mass system, which is kind of a Lagrangian approach that we are doing, this is equal to the time rate of change, okay, of this in the control volume. I'll explain what a control volume is and basically this is the rate of change of the property inside the control volume. So we typically write it as integral over the entire volume rho times small n times dv. So this is basically the rate of change of the property inside the control volume. Okay, this is rate of change of n inside CV. CV means the control volume plus, the efflux. The efflux term, we kind of write it as the control surface integral of this control surface integral. I kind of write it as this, and this is rho n v dot n hat t. That's it. That typically is your Reynolds transport theorem. Okay, so what it says is that if you have an extensive property defined in a Lagrangian system or in a control mass system, this is equivalent to finding out the change inside a control volume in an Eulerian system plus the efflux. So the efflux means anything that is coming in minus the anything that is going out. This is typically known as efflux. Okay, so when we solve this problem, the application of this Reynolds transport theorem would be clear to you. Okay, but this is typically what the most generic form of Reynolds transport theorem looks like. Okay, now let's look in this problem and try to use the Reynolds transport theorem here. So what it says is, it's a very standard and a very simple problem. It says that there is a tank which was initially empty, and you start filling water inside this tank. Okay, and the water that comes inside this tank comes through these two pipes. As you can see, they're denoted by 1 and 2. Okay, so it's like you're connecting two pipes inside this tank and you start filling, you start putting water inside. So naturally what will happen is the water level will typically rise, as you can see, and at any instant of time this water level has a height h. I hope you can realize that since there is a net inflow without any outflow, this means that the water level inside the tank would typically rise with time. That's an obvious thing, right? It's an obvious thing that you can see when you observe this problem. So that's the given problem. Okay, for the sake of simplicity, you can assume that these v1 and v2s, this v1, maybe I'll write it like this, this v1 and v2, okay, these are uniform, so they possess uniform velocity profile, which means that if you kind of zoom in, so if you basically zoom in inside this pipe, the variation of velocity, if you basically zoom in, maybe I'll draw it like this. So basically if you take this section and take a zoomed in version, you will kind of see the pipe like this. Okay, maybe I'll draw it with a different color. You'll see the pipe like this. What it means is across the cross section of this pipe, your velocity profiles are uniform, meaning that your V2 or V1, both of them would vary uniformly inside the pipe. Okay, I hope this is clear. This is what its variation is going to be. This is what V2 or V1 is going to be. So it is not varying along the cross section of this pipe. Okay, this is something that I wanted to infer. Okay, all right. So given this scenario that there is a tank which was initially empty, you started putting water inside the tank using two pipes. The velocity of water inside the pipes that is coming inside the tank is given by V1 and V2. Their respective areas are A1 and A2. You simply need to give me an expression that what is this H as a function of time is going to be. That's it. That's all that we are trying to do. Okay, I'll again stop here for a couple of minutes. If there are any questions, you can ask me on the physical description of the problem.
I will look once, sir, because since I'm new to this
Yeah.
subject,
Okay.
so I will look once again. So if there is any, I will ask in next sessions.
Yeah, yeah, of course, of course. So I would suggest you. So this I was telling in the. So basically, this is something that I was telling in the previous. I mean, some time back. I thought you didn't join at that time, but anyways. So
Yeah.
the point is, yeah. So the point is like before coming to this discussion session, it is advisable that you look into the lecture series video of this week basically, because the concepts, the nuances or basically the theory, these are taught in the lecture series. And
Okay.
in these discussion, or we kind of like do the problems that is associated with the concept that had been taught in the lecture series. Okay, and if there are any doubts, then we'll address in the discussion session. So
Yeah.
that's the
Yeah.
idea
Okay.
behind
Okay.
this. Okay, but anyways, like feel
Okay.
free to let me know if you have any doubt at any point of time. Okay,
Okay. Okay. Okay.
yeah, anyways, okay.
Can I get your anything like personal mail ID or something? Anything?
Actually, we are not encouraged to share our personal details because this is kind of a public. So we are basically doing this in public domain. So
Okay.
the point is, what you can do is there is something known as, so this I forgot to announce in the beginning. So there is something known as the discussion. So I think it's called. So in the course website, there is something known as a discussion group or something like this. Okay, discussion something like this. I forgot the name, but it's written I think Q&A or discussion something like. So what you can do is if you click there in the course, you will open a Gmail thread where you can ask your questions there, and your questions will be directly posted there, and we'll answer the questions there and then and there itself. Okay. I think
Okay.
it's called discussion forum. It's written as discussion forum. So if you go into the course website and click on the discussion forum, you will open a page. I think that is linked to Gmail where you can directly post your doubt there. Okay,
Okay.
and
Okay.
we
Okay.
from the NPTEL team will address your doubt through that forum only. I mean that's what
Okay.
we are asked to do basically. Okay.
Okay. Okay.
Okay. All right.
Yeah.
Okay, so then let's solve this. As I was telling, so what we need to do is basically we need to apply the Reynolds transport theorem as we had been discussing, and then what we'll do is we will kind of choose. So what we'll now do is we'll choose the extensive property, this n, as mass. Okay, we'll choose this n as mass. See, the idea is that what basically will happen here is that when the fluid comes in, physically what it will happen. So there are two pipes through which you are putting, let's say, water in. See, whatever the water that comes inside this tank, as a result of that, the height of the water inside the tank would rise. So ultimately it's a mass conservation thing that is going on here, right? It's just the mass conservation thing, but it's the more formal way of writing the mass conservation. That is something that I would say when you use it through the Reynolds transport theorem. Okay, so that's what we'll do. So we'll choose n to be equal to m, and then your small n basically becomes equal to 1. And then if you apply this into this Reynolds transport theorem, basically if you apply this here, what you will get is dm by dt That's the right hand side of a control mass system. The small n is just equal to 1, so I can write it as del T of integral over the volume rho times dv, where v with a cut is something that I saw. So this basically denotes volume. Don't confuse it with anything else. This is just the volume basically. So this means that I'm basically integrating it over the entire volume of the tank. That's what I'm doing. Okay. Plus the efflux, which is integral over the control surface rho v dot n hat dA. Okay. Now before proceeding, we need to look into two key aspects. Okay. One is, first of all, we need to choose a control volume. So what I will do is, as we had been doing it in the I mean in multiple examples, in if you had a chance to go through the lecture series, what we do is we basically choose a control volume that will encompass the water inside the tank, that is flowing inside the tank, along with the two inlets basically. So this is something that I will choose as my control volume. Okay. So this red zone will consider, so basically this will take into account all the water that is inside the tank plus the two inlets through which water is coming inside the tank basically. Okay. And then this red zone becomes my control volume. This basically becomes my control volume. Okay. Then I hope you understand that the control surface now is the control surface is the surface that encompasses a control volume. For instance, it's like if you think of a balloon to be a control volume, so the air inside the balloon would so if you think of like the air inside that, so basically the air that is present inside the surface of a balloon to be a control volume, then the surface of the balloon is the control surface, and the inflow is the point through which you pour air inside the balloon basically. That becomes the surface through which the external mass is coming inside the control volume. The same analogy is basically drawn here. You have the control volume encompassing the water, and there are two inlets in the control volume. The two inlets is where water comes inside the control volume. That's the whole idea behind this control volume. Okay. All right. So then if I write this Reynolds transport theorem, I can, so first of all, this term dm by dt in a control, so this CMS means a control mass system. And if you use mass conservation, you can directly show that this is equal to 0, because see, a mass system or a control mass system is where your mass is conserved. That means that your mass cannot change with time basically. Okay. In a control mass system or in a Lagrangian frame of reference. Okay. Which means all I end up is 0 equal to del T of integral of rho times dv plus integral over the control surface rho v dot n hat dA. Okay. Now let's systematically, sorry. Now let's systematically evaluate these two quantities. Okay. So the first quantity, let's first evaluate the first quantity. Okay. So one assumption that I'll assume here is that your density is equal to constant, which means I can then take density. Constant means your density is not a function of space, and also it's not a function of time, which means then I can take this density outside the integrals, and then since there is a 0 outside, I can then cancel a density from the two sides basically. So it then simplifies to 0 times del T of this integral over v dv plus integral over the control surface v dot n hat dA. Okay. Where you need one more quantity here. This AT denote the cross-sectional area of the tank basically. Just remember this. Okay. So A1 is the area of the inlet pipe 1, A2 is the area of the inlet pipe 2, and AT is basically the cross-sectional area of the tank. Okay. All right. So then what we'll do is this quantity. It is based. So what does this quantity say? It says that in this tank, okay, just try to understand this. Okay, in this tank, if I pick a differential volume, so how does a differential volume look like inside this control volume? So a differential volume would basically look like this, right? So maybe I'll draw another picture and try to explain it to you. So this was typically my control volume. Okay, maybe something like this. This was my control volume, right? So if I now pick a differential volume inside the control volume, what I would say is at a particular, let's say y, I will pick a strip, okay, and let's say this strip is basically the thickness of this strip is equal to dy. But I know that, see, there is one thing, right? I know that the height of the water is itself changing with time, right? Which means that I can denote my y, which is, I mean, I can denote my y coordinate as just h of t. That it is basically the instantaneous height of water that I have. Okay. So then this quantity integral over the control volume dv is going to be the area of the tank times h of t, right? This is what is going to be the instantaneous control volume. Because I hope you can understand that your water inside the tank that is present is what is the volume of the control volume that we are considering, and this is equal to how much height of water, I mean how much of this height of water it has attained times the cross sectional area of the tank. Right now the cross sectional area is basically constant. You cannot change the cross sectional area. The only thing that you can change is the height of water that is basically coming inside the tank from the two pipes that is connected. And that is where you can write this integral v over dv that we have written as the area of the tank times h of t. So I hope you understand that the volume, that the control volume here itself is a function of time. That is typically because I'm considering the water that is coming inside as my control volume typically, or the water that is present to be more accurate. I'm considering the water that is present inside the tank to be my control volume. This makes your control volume a function of time. Okay, which means that this quantity then just simplifies to 0 equal to del del t, and integral over a differential volume times dv is going to be just the volume of the control volume, which means the area of the tank times h of t plus the other term, which is integral over the control surface v dot n hat dA. Okay, I hope you are clear with me on this point. All right, we are still left to evaluate this term. This will do once this term is sorted. Now you need to understand that this at is the area of the tank, and this is just a constant, which means I just end up getting 0 equal to at times d of h by dt. That is simply because I can now replace this partial derivative as an ordinary derivative, because I know that the height of the tank, it is just a function of time. It is not a function of space. Okay, or I should say the height of the of so in correct sense I should say it is the height of the water level inside the tank, which is just because that is what we are choosing it as a control volume, right? So this means that the height of the water level inside the tank is just a function of time, and that's the reason why we are replacing this del with the simple d operator, because now it just becomes an ordinary derivative of time. Okay. Okay, then we have simplified the first term. The second term is left to be simplified, which is the control surface integral of v dot n hat dA. Okay, so now let's simplify this term. So for this, you must understand. So we'll go back to our control volume itself, which is this case. So you can now see that inside the control volume, there are two ways through which water is coming out. Okay, so this was your control volume, and through this 5 you have water coming out with velocity v1, which is uniform, and through this 5 you have water coming in with a different velocity v2, but this is also considered to be uniform. So if this is my control volume, then I hope you realize that this dotted line is my control surface. It's the same balloon example that I gave you, right? The air inside the balloon is your control volume, and the surface that is encompassing the air, that's your control surface basically. Okay, and in a balloon you have just one inlet. Here we have two inlets basically. So this means if I want to integrate this over the control surface, I must now focus my attention to these 2 points only, because at any other point on the surface there is nothing that is coming inside the control surface. Okay, so then I will basically now focus on these two areas. The area, the pipe which is leading the water inside the control volume, and the same thing at the cross section V2. Okay, So let's look at the cross section 1 first. So in 1, I have something like this. So I have this pipe and then I have this tank. I'm just drawing this bit, okay? And then I have water basically that is filled inside the tank. Okay, so this is what it looks like typically, where this is what is V1. So now if and you remember this was my control surface. This dotted lines was my control surface. Okay, so if I want to evaluate this quantity, integral this v dot n hat dA, this would simply, so I need to look into two aspects. One, the normal of this area that I am integrating over, and second, the direction of the velocity vector. I hope you can realize that your velocity vector is coming inside the control volume, but the normal is basically the normal of the control surface basically, and this always points outwards of the control volume. Okay, because your surface, so it's like it's a normal that is pointing outward of the surface. So my unit normal in this case would be in this direction. So this would be the direction of n hat when you are looking into the first inlet. This clearly means that if I do a dot product between this velocity and this unit normal, their dot product is going to give you a negative sign. That is typically because the two vectors, one the velocity vector and the unit normal, they are yes, they are collinear, but they are of opposite signs basically. The direction of the two vectors are not the same. In fact, they are just opposite to one another, which means that for cross section 1, this v dot n hat dA is just going to give you v1 a1 but with a negative sign. The reason is, again, if you do that, so it's like if you do the dot product, it is going to be magnitude of v. So if you do the dot product here, and if you use the fact that a dot b is equal to mod a times mod b times cos of theta, but remember theta is the angle between the two vectors, and you know that in this case your theta is equal to 180, right? And that's the reason why you end up getting a negative sign when you evaluate this v dot dA. Okay, in the same spirit, I repeat, if you do the same exercise for the second outlet, you will see that it will also come out to be equal to v2a2. See, the reason again is just straightforward, just like this. If you look into, so if you zoom into this area, okay, you will see that your velocity is in this direction, the normal of this area is in the outward direction, that is in the other direction. And that's the reason why when you simplify this for the outlets 1 and 2, you will see that you will just end up getting minus v1a1 minus v2a2. Okay, so this is typically the efflux term. This term we call it as the efflux term. Okay, that's it. We just now need to substitute this into the Reynolds transport theorem. Okay, so then this becomes 0 equal to AT times TH dt. Okay, and then we have minus V1A1 minus V2A2. And remember, we just require an express. Basically, we just require how it increases with time. The other side, all the other side to the left hand side, and we'll just get dH dt equal to V1A1 plus V2A2 divided by AT. Okay, that's it. So you can see that all of these are constants. V1 is a constant, A1 is a constant, V2, A2, these are all constants, which means that I can simply integrate this and I will get H equal to V1A1 plus V2A2. Or maybe you can do it like this. So first let's write it as dH and then this would be AT, and then I take the dt here and then I integrate it. So at time t equal to 0, I know that my H was equal to 0. I didn't have any control volume. I want to evaluate this at time t, and then this becomes H of t, which means your H of t is just going to be, and remember this is just a constant, right? So this will just come out of the integral. This is going to be V1A1 plus V2A2 divided by AT times of t. Okay, that's it. That's typically how your height inside the tank or your water height inside the tank is going to vary with time. That's your answer. And I hope you understood how basically we apply the Reynolds transport theorem. Okay, So the important part in this exercise is this quantity, I would say, calculating the efflux term from the control surface, like identifying the direction of the velocity and the direction of the normal, and then using, I mean, acknowledging the fact that your normal is pointing outward of the surface while your velocity is pointing inward of the surface. So you can now make a general statement. In any control volume, if you have an inflow, your v dot n hat is always going to give you a negative sign, because you know that your inflow is coming inside the control volume and your n hat will always face outside the control volume. That typically, because we consider n hat to be going radially outward of the control surface, meaning that their dot products are always going to give you a negative sign. If you have an outflow of the tank, for instance, like in your assignment, there is a question where your water height is fixed and your fluid is coming in and a fluid is going out separately. In that example, in the outflow pipe, we will see that your v dot n hat is a positive sign. Okay, so I will encourage you to solve that problem in the assignment, and let me know if you have any doubts in that problem. Okay, again I said I will not exactly solve the problem that is there in the assignment. That is because that doesn't serve the purpose, right? This is something for you to do, but I will always solve problems that are very close to the ones that are there in the assignment, such that if you solve these kind of problems, you can easily do the problem that is there in your assignment. You need to be a little bit careful in your assignment problem, because in one of the pipes your velocity profile is basically not uniform, so you need to integrate that velocity profile from the point from the downward section of the pipe towards the upper half of the pipe. Apart from that, the problem in your assignment is exactly same as the problem that we have done here. Okay, but the only difference, as I said, is that okay, in one of the pipe the velocity profile was varying. The second thing is that you have an inflow and an outflow, so the net head of water, that is h that we have written here, that remains constant in that problem. Okay, so I hope you realize that in that problem you just need to evaluate this quantity. That's it. That's all that you need to do. So I'll encourage you to have a look at that problem. I think I have typically showed that yeah, so this is what the problem would look like in your assignment. I'll not solve this problem today, but I'll show you how to solve this problem once you try this problem on your own in the assignment. And then if there are any doubts, as I say, please post it in the discussion hour, and I'll try to solve this problem if there are any doubts in the next discussion session. But the idea is, the application that I said, you exactly need to apply this Reynolds transport theorem as I have shown you in this class, or like in this discussion hour. Okay, so maybe we will stop here for today, and I thank you for the viewers who have joined this session. That is the first session, and please go through the lecture series, and please actively participate in the discussion hour. If there are any questions, post it in the discussion. In the discussion forum of the course, and also try to join in the discussion hour such that we can clarify your queries then and there itself. Okay. Once again, I thank you. So we will meet.
Yeah, okay, thank you.
Yeah. Okay. All right. So we'll meet again on next Saturday at the same time using the same link, basically. Thank you guys. Thank you for joining. See you all in the next week.